A charging port appears to be an absence, a narrow opening in plastic or metal, a dark slot edged with polished steel. Inside a thin strip of contacts, almost delicate, it does not draw attention. It is simply where power goes in. But that small opening is one of the most constrained design spaces in modern consumer electronics. It carries electricity, data, mechanical stress, heat, and human error, all within a few millimeters. Before standardized charging ports, devices were islands. In the early days of consumer electronics, each manufacturer designed its own power connector. Radios, early mobile phones, laptops each had proprietary plugs. Barrel connectors were common, cylindrical plugs with a center pin delivering positive voltage and an outer sleeve acting as ground. Barrel connectors were simple and robust, but they carried limitations. They were often bulky. Their polarity had to match precisely. If a user inserted the wrong adapter, voltage mismatches could damage circuits. There was no universal communication between charger and device. Power flowed at a fixed rate. This system worked in a world where devices were fewer and larger. Then electronics shrank. As mobile phones became slimmer and laptops thinner, space inside devices became scarce. Every millimeter mattered. The connector could no longer be a large cylinder protruding from the side. It had to flatten, shrink, and align with tighter internal layouts. At the same time, devices began doing more than charging. They needed to transfer data, photos, music, files. Instead of separate ports for power and data, engineers saw opportunity in combining them. USB emerged as that unifying standard. The original USB-A connector, introduced in the mid-1990s, was designed primarily for computers. It was rectangular, robust, and polarized, meaning it could only be inserted one way. Inside, flat metal contacts aligned with matching pins in the socket. The shape solved a specific set of constraints. It needed to be strong enough to endure repeated insertion. It needed to prevent incorrect polarity. It needed to shield data lines from interference. It also needed to be inexpensive to manufacture at scale. The metal shell acted as structural reinforcement and electromagnetic shielding. The plastic tongue inside carried the actual electrical contacts. That tongue appears fragile, but it is supported by the surrounding housing and carefully aligned to distribute stress. When USB migrated from computers to smaller devices, mini USB and later micro USB were introduced. These connectors shrank dramatically. The port became thinner, and the internal tongue became narrower. Here, the design constraints intensified. The port had to survive thousands of insertions and removals. Users plug cables in without looking. They pull them at angles. They trip over cords. The connector must tolerate torque and shear forces without ripping off the circuit board inside the device. This is where the metal shell matters. The shell absorbs mechanical stress before it reaches delicate solder joints on the motherboard. Tiny retention springs inside the port create friction, holding the plug in place. That friction must be strong enough to prevent accidental disconnection, but weak enough to allow easy removal. Every millimeter inside the port is engineered for compromise. Then came a major usability problem: orientation. Micro USB could only be inserted one way. In practice, users frequently attempted insertion upside down. This caused frustration, wear, and occasionally damage. Human behavior revealed the flaw. People do not carefully inspect small ports before plugging in cables. They rely on muscle memory and speed. The aha moment in charging port design arrived with reversibility. USB-C, introduced in 2014, eliminated orientation frustration by making the connector symmetrical. It could be inserted either way, but achieving this required more than flipping the shape. Reversibility meant duplicating internal contacts. It meant designing a port where the internal tongue remained centered while contacts were mirrored. It meant ensuring that power and data lines could negotiate direction dynamically. This required intelligent communication. Modern charging ports no longer passively deliver electricity. They negotiate. When a USB-C cable connects, the device and charger exchange signals. They determine voltage levels, current limits, and data roles. Power can flow in either direction. This evolution reveals a deeper shift. Charging ports are no longer just mechanical connectors. They are communication interfaces. As devices demanded faster charging, the physical constraints tightened further. Higher power delivery means more heat. More heat means greater risk of damage. The connector must dissipate heat safely while maintaining structural integrity. USB-C's oval shape is not aesthetic, it balances strength and compactness. The rounded edges reduce stress concentration. The internal tongue is shorter and reinforced. The symmetrical pin layout allows flexible data routing. Why does the charging port look hollow rather than solid? Because airflow and spacing matter. Electrical contacts must be insulated from each other. The housing must prevent short circuits. The open cavity allows precise alignment between plug and port. Tolerances are measured in fractions of a millimeter. There is also a trade-off between durability and thinness. Consumers demand thinner phones and laptops. Engineers must fit batteries, processors, antennas, cameras, and still reserve space for a port capable of delivering up to 100 watts or more. The connector cannot grow proportionally with power needs. So materials improve instead. Stronger alloys, better plating, reinforced solder joints, anchor points within device frames that distribute force away from circuit boards. Even the placement of the charging port on a device reflects human behavior. Most phones position it at the bottom edge. This allows upright charging on surfaces and ergonomic cable routing during use. Laptops often place ports along sides to balance structural ribs and internal battery layout. Charging ports also reflect regulatory and industry pressure. For years, proprietary connectors persisted because they locked consumers into ecosystems. But interoperability became valuable. Standardization reduced e-waste and simplified manufacturing. Governments began pushing for universal charging standards. This influenced design evolution as much as engineering did. There is an invisible battle inside every charging port between electrical performance and mechanical survival. Contacts must be plated with conductive materials that resist corrosion. The port must survive dust, lint, and pocket debris. Many modern failures are not electrical at all, but mechanical. Lint compresses inside ports, preventing full insertion. That small cavity becomes a collection point for daily life. And yet the port persists. Why not eliminate it entirely? Wireless charging attempts exactly that. It removes the physical connector and transfers power via induction. But wireless charging introduces inefficiency and heat. It requires precise coil alignment. It cannot yet match the speed and stability of wired charging at high wattage, so the port remains. The deeper realization is this: the charging port is shaped less by electricity than by human imperfection. We plug cables in at angles, we yank them, we carry devices in dusty pockets, we demand speed and thinness simultaneously. The port must survive all of that. Its metal frame protects internal solder points. Its internal tongue aligns contacts precisely. Its symmetrical shape acknowledges that we do not like thinking about orientation. Its negotiation circuitry protects against overload and mismatched chargers. It looks simple because its complexity is hidden. Inside that small opening, multiple systems coordinate: mechanical, retention springs, shielding layers, power controllers, data switches. The form we see is the outermost layer of a dense compromise. And the fact that charging ports keep evolving is not a sign of failure. It is a sign that constraints keep shifting. Devices get thinner, power demands rise, data speeds increase, regulations change. Each new generation of connector reflects updated constraints. The original barrel plug solved a world of isolated devices. USB solved a world of expanding connectivity. USB-C solves a world of high power and bidirectional data. The port's hollow shape is not emptiness, it is tolerance space. Tolerance for heat, for misalignment, for wear, for human haste. Invisible design often hides where we least expect it, in the gaps rather than the objects themselves. The charging port exists in its current form because it survived physics, economics, regulation, and behavior all at once. When you plug in your device without looking and it connects instantly, that small success is the product of decades of refinement. A narrow opening, precisely shaped, carrying far more than electricity. And like many mature designs, it disappears into routine until the day it fails. Then we notice how much engineering was quietly holding everything together. That is the mark of invisible design, not dramatic, but essential.